On Monday, we started talking about addition reactions. And as you saw, there were many different reactions. Some of them share the same type of mechanisms. So it's a good idea that you think of them as reactions that can be grouped. Like, for example, you can think of the halogenation in where we add an H on one side and an X on the other side, having a very similar mechanism as the hydration where we add an H and an OH on the other side. And you can do that for the rest of the reactions. Some of these reactions in this scheme you may have not seen, but I'm going to go through them today. And as I was saying, there are many, many reactions that can be done starting from an alkene. We're not going to see all of them in the course, but we're going to see a good amount of them. So just this is just to give you an example of the amount of reactions that we could do just starting with a simple alkene like this one, the versatility of alkenes. As a reminder, let me restate what the addition of an HBr was and the mechanism for that. So we started with an alkene, and one of those pi bonds would break, and also that HBr sigma bond is going to break, and then at the product, we're going to end up with two new sigma bonds. One is going to be the CBr, and the other one that it's not shown here is that CH new bond. The way that this reaction proceeds is the alkene that is a nucleophile will attack the hydrogen, and because hydrogen can only form one bond at a time, then the Br, that you know that it's a good leaving group, is going to leave. Then we can get two possible carbocations. Remember, we could go through this one, or we could go through this other carbocation, depending if the H ends up there or the H ends up there. Remember, everything that you know about carbocations is still true here. So here in this left side, we have a tertiary carbocation, and on the right side, we have a secondary carbocation. So the tertiary is much more stable, and remember that Hammond postulate that says that the product is going to resemble the intermediate, and therefore the secondary carbocation is not going to be the root is going to be the tertiary one, and now we have the Br minus that is going to come back and attack, and that's how we end up in with the Br in the more substituted alkene. Remember that that was called the Markovnikov type of mechanism, or the Markovnikov product, in which the Br or my nucleophile will end up in the more substituted position. Here is the energy diagram for a simple addition reaction. In the first step, we have that proton transfer, and remember the activation energy is the highest one because it's the formation of that carbocation, that intermediate. And the second one will be the nucleophilic attack of the Br to that carbocation that takes less energy. That's why this activation energy is smaller. You must also remember that because we go through a carbocation, it is possible that we get hydride or methyl shifts. Remember that the carbocations are always going to try to rearrange to give us the most stable intermediate possible. We've seen that for SN1 reactions, we've seen that for elimination, and the same is true for additions now. And another characteristic of carbocations that we've seen in previous chapters, is that because we go through a carbocation, that carbocation can potentially be attacked from either the top or the bottom, and that's how we're going to get two products. One is the R and one is the S. Because if you look at this reaction right here, and we end up with that carbocation is sp2 hybridized, which means that it's a flat carbon, and that carbon, if it looks like, if you imagine it being flat like that, So in this side, we're going to have only one carbon, and the other side, we're going to have two. So if you imagine that being flat, it could either be attacked from here, from this with the Cl, or here. And that's how we get the R and the S molecules, because we form a new chiral center. But sometimes we're going to need our molecule to present the anti-Markovnikov product, which means that the Br, my nucleophile, is not going to end up in the more substituted carbon, that will be this one, but instead it will end up in the least substituted carbon. This is what we call the anti-Markovnikov product, and we see it when we treat the alkene with HBr, just as we were treating it before, but we add peroxides now. Anytime you see peroxides with HBr, you must think of an anti-Markovnikov type of product. And so if we look at one example right here, you see we have HBr, but do not be mistaken, because here we have those peroxides, and we know that peroxides are a sign of anti-Markovnikov. You don't have to memorize the mechanism, but what you must know is that the Br is not going to end up there. It's going to end up in the least substituted carbon across the alkene. So that's how we end up with the Br right there.